the sheet. So we're going to continue with our work on Fourier series. We don't have too much left to do, just a lecture or two, I think, on the kind of new material. Before I do, though, I just want to briefly mention a point. So I saw half of you last Friday in the maths methods tutorial, and it's just we left a point hanging in the air then. So apologies to everyone who wasn't there, but I'll just settle this point, because it is useful for everybody. So, but it's on the linear algebra. We were looking at these examples of possible inner products on vector spaces of matrices, and the question came up, was the trace of a product of two matrices, was it equal to the trace when you take the product the opposite way around? So this is for AB square matrices of some size n. So this is the symmetry condition. This is the symmetry condition for the inner product of two matrices defined by the trace function. So I raised this point in the class, and I said I thought it was true, but then I thought it wasn't true, and then I tried proving it, and I couldn't really get it. So just sort of settle this. Now, it is true. I don't know why I went a bit wobbly with the proof on Friday, but what I had on the board was more or less the proof of it, so I'll just do it quickly for you now. So the trace of any matrix, of course, is defined as the sum over all I of every diagonal entry. So this is the sum over all the indices I of the entry II. So this is the 1,1 entry of the matrix, the 2,2 entry, the 3,3 entry, and so on, all the way down to the NN entry. So these are the entries in the leading diagonal, the diagonal from top left to bottom right. But now, what's the ith entry of a matrix product? Well, the ith entry of a matrix product, well, you have to multiply the ith row from A into the ith column of B. So this will be the sum of all these products, Aij, Bji, summing over J. This is just the formula for the ith entry of a matrix product. Okay? The elements Aij are all the elements along the ith row. The elements of A, the elements Bji, down the ith column of B. And it's just like, yeah. I stumbled over this part of the proof. This is a double finite summation of a bunch of numbers. You can think of these numbers, see, they're indexed by two indices, I and j, so you can lay them out in a rectangle, just a big rectangle of numbers. And when you've got the double summation here, sum over I, sum over j, that would correspond to, so if j is the index which is going across the rows, then, or which is going which is indexing the rows, then this inner sum is the sum of the columns of that rectangle, and then you're adding up all those column sums. But you can, with a rectangle of data, you can just switch it all around and instead sum it in the opposite way. So if you had a big grid, a big two-dimensional array of numbers, one way of counting it would be to sum up all the columns and then sum up all the column totals. Then you'd have the sum of all the numbers in the array. But equally well, you can instead sum up all the rows. So you evaluate the sum of one row, evaluate the sum of the next row, etc., and then sum up all the row totals. That still gives you the same number, the sum of all the numbers in the array. So we got the sum over j on the outside now, and the sum over I on the inside. Now, this, when you just focus on one of these products here, this is just a product of two real numbers, aij times bji, so we can change the order of those without any difficulty, because it's just multiplication of real numbers, that's commutative. But now, what's in the round bracket there is exactly the entry, the entry jj of the matrix product B times A. So these are the entries on the leading diagonal. J equals 1, we've got the 1, entry. J equals 2, we've got the 2, entry, the 3, entry. So these are all the entries on the leading diagonal of BA, and we're summing over all J. So that is the trace of BA. So it is true. So yeah, I won't dwell too long on this. This question came up because we were investigating a possible inner product defined by this trace function. It isn't an inner product though, because it fails some of the other properties, either the linearity or the positive indefiniteness. But it is symmetric. Okay. So although matrix multiplication is not commutative, B times A is not the same as A times B, but of course that's not to say that there isn't any kind of relationship between those two different matrix products. They're still quite intimately connected. They've got the same determinant, for instance. The determinant of A times B is equal to the determinant of B times A. And here you can see they've got the same trace. I think they'll have the same eigenvalues, I think, just off the top of my head, although probably different eigenvectors. And so on. Okay. Any questions just quickly on that point before we move on? So that's just to settle something that arose in my tutorial last week. And I wouldn't normally do that in the lecture, but because I was half of you I had in that Friday tutorial, I thought I'd do it there. Okay. So we shall move on back to Fourier series and just pick up with where we were last time, which we were looking at odd and even functions. So just a quick review of the definition. An even function is a function which behaves like this. F of minus x is always the same as f of x. An odd function is one which has this behavior. For every real argument x, f of minus x is equal to minus f of x. So we spent some time investigating these definitions. And these two properties really affect integrals. When you integrate these functions across an interval centered at the origin, odd functions have an integral of 0, and even functions have an integral which is twice the integral just over the positive half. Okay, so we spent some time exploring that last time. And the consequence of it is because cosine is an even function and sine is an odd function, and because, you see, we had a previous theorem which dealt with what happens when you multiply together odd and even functions. So theorem 3.2, we proved last time. Product of two even functions is even, product of two odd functions is even, and the product of an even and an odd is odd. Now this is quite confusing because even and odd, as it's used for integers divisible by 2, does not behave like that. Product of two odd integers is an odd integer. The product of two odd functions is an even function. So it is kind of a slightly confusing double use of terminology, but that's where we are. So the consequences for Fourier series was contained in these two theorems, theorems 3.4 and 3.5. They didn't need separate proofs themselves. They were more or less proved by all the previous proofs. It's just kind of combining all those properties. And these said, and we're going to work through an example now. So there's an even one, and there's a theorem for even functions, theorem for odd functions. If the function g you're looking at is an even function, the Fourier series that you see for an even function is always one of this form. So the sine functions are completely absent from it. it'll only have the constant term at the front and then a summation involving certain cosine functions. Some of these coefficients an could still be 0, of course, but we know for definite that the bn coefficients are all 0, so we can just completely forget about the sine functions. They won't take any part in the Fourier series of an even function. And correspondingly, for an odd function, here in theorem 3.5, when h is an odd function, its Fourier series will just look like this. There won't be any cosine functions, and there won't be any constant term half a0 on the front side. Okay? You only have these bn times sine. Now, some of these bn's, of course, could be 0, but we know for definite that all the an's are. Okay? So this kind of thing, take this kind of series in 3.23 here. This is called a sine series because it only consists of sines. This one up here will be called a cosine series. So it only consists of cosine and maybe a constant term as well. So we can kind of use these results to our benefit as a kind of bit of foreknowledge about what the Fourier series is going to be like, and it can kind of more or less have the amount of work that we have to do, because we automatically know that 1/2 of the coefficients are 0. So we'll look at this example 3.7 now, which is working with the function f of x equals x squared. And yeah, we'll explore this example a little bit. Any questions about the definition of odd and even function or any of those results about it, first of all? Anything that I can clear up or clarify for you? Okay. All right. So example 3.7. So this will be to use the concepts of odd and or even functions to obtain the Fourier series of the function f of x equals x squared. I don't think we've worked through this example before, but just to see it. So here's the solution. So first of all, can we classify this function? Is this function an odd or an even function? How is that function going to behave when you throw an argument 5 at it and you throw the argument -5? So when you throw positive arguments and minus negative arguments of the same magnitude at that function always reports the same value because it's the square of x. So clearly, f is an even function. Even function, as when you evaluate it at -x, you get -x squared. Of course, that's equal to x squared, which is, of course, equal to f of x. And those equations are true for every real number x. So that's true for every real x. Complex x, to be honest, as well. Most kind of algebraic systems have -x squared equal to x. So we're dealing with an even function. So we look at our bank of results about Fourier series for odd and even functions. So this means its Fourier series has no sine functions, i.e. bn coefficients are equal to 0 for every value of n. Understood that bn is the Fourier coefficient on the sine functions. Yeah. So that immediately kind of halves the amount of work we have to do. We already know that the bn's are 0. And if you go back to the reasoning, back to the chain of results, the reason they're all 0 is because to work them out, you have to take the inner product of the sine function with f. So the inner product of the sine function with f in this context is the integral of f multiplied by the sine function. So you're multiplying an even function x squared times one of those sine functions, which is an odd function. So overall, the integrand there, f times the sine function, is an odd function. So you've multiplied even by odd. That gives you odd. So you're integrating an odd function across an interval centered at the origin. Odd functions have the exact opposite behavior either side of the origin. It's positive on one side, it's going to be negative on the corresponding bit on the other side, and so on. So when you integrate it across something centered at the origin, because every bit on one side is mirrored by a bit of the opposite sign on the other side, the integral is going to be 0. Okay? Because all contributions cancel out with a similar contribution of negatives of opposite sign on the other side. That's just kind of quickly going through the proof again in words. But it's good to remind yourself. But that won't be automatically so for the AN coefficients. So we should go and work those out. So we expect a Fourier series. We expect a Fourier series for f looking like the f of x is x squared, and this is going to look like a half of a0 for some value of a0 plus the sum of an times cosine nx. So this is over every n bigger than or equal to 0. Okay. So that's the kind of Fourier series we expect. It's parameterized by this a0 and these ans, which we don't know yet. So let's try and obtain those. So first of all, the constant coefficient, or 2 times the constant coefficient, which is a0. This is it's the integral simply of the function f itself. But since we know we're dealing with an even function, rather than this being the integral from minus pi to pi, we can instead express it now as the integral from 0 to pi, simply just over 1/2 of the range, and it will be 2 over pi times this. Okay. Normally, the integral you expect to see here is 1 over pi times the integral from minus pi to pi. But because f is an even function, we know that integral over the whole interval minus pi to pi will just be twice this one. 2 times the integral over the positive half of the domain. So this is 2 over pi. So f is the function x squared dx. Okay, this is very basic integral. This shouldn't give us any problems at all. This integral comes out as 2 over pi times x cubed over 3, evaluated at 0 and pi. So it's just a matter of sticking pi in for x. So it's going to be 2/3 of pi squared, I guess. Yeah, 2/3 of pi squared. So that's a0. So that means the constant coefficient in our Fourier series will be 1/2 of this, so 1/3 pi squared. Box around our a0. We've determined a0. Okay, so then we will turn to all the other a coefficients. A0 is a special case because you're just integrating function f itself. For the other ans, you'll be integrating f times the corresponding cosine function. So it makes sense to do those all together. Or hopefully we can deal with those all in one go. So now when n is bigger than or equal to 1, Fourier coefficient an, again we'll use the form of the definition which applies to even functions. Okay, so that's just the normal, that's the formula for the Fourier coefficients an for an even function. So we want to integrate this out. This is 2 over pi times the integral from 0 to pi of x squared cosine nx dx. Well, okay, yeah. Now that integral might be in the formula booklet, the integral of x squared times cosine. It might be one of the standard integrals that's presented in the formula booklet. But if you don't have a formula to hand for that, you can get it out of more basic results by using the process of integration by parts. Okay, it's slightly tricky at the moment if you don't have the formula for it, because you have to integrate a product of two different functions, either an x squared or the cosine of nx. But the technique we typically use for dealing with products of functions to integrate them is integration by parts. It's the corresponding result to using the product rule for differentiation, of course. Integration by parts is. They're the same result, really. So you have to look at this, and you have to recast one of these factors as a derivative of something, and with the other factor, which you leave as it is, you hope that after integration by parts, it's going to look a bit simpler. So the one we want to simplify away in a couple of steps maybe is the x squared factor. So we want to keep hitting this with integration by parts, and eventually it'll turn into an integral of maybe a cosine or a sine. The cosine factor at the moment we can easily write as the derivative of something. It's the derivative of an appropriate sine function. So that looks to be the way to set it up for integration by parts. So it's 2 over pi integral from 0 to pi of x squared. So this will be d dx of sine of nx over n dx. And then use integration by parts. That make sense? Any clarification required on that? So let's go ahead and do that. So we've got this factor 2 over pi here at the front. This shows a large pair of brackets because that 2 over pi has to multiply into everything. Then we'll have x squared times sine of nx over n, evaluated at 0 pi. And then we'll be subtracting integral from 0 to pi. And now we'll be differentiating the x squared factor to become 2x. And we'll be keeping the sine nx over n there. I'll simplify it a bit as I go. So I'll have an extra factor of 2 from differentiating the x squared. I get 2 times x. And I've got this factor of n here. I'll bring those outside the integral to make it a little bit easier. So it'll be minus 2 over n times the integral of x sine nx dx. Okay. So that's what the application of integration by parts once. So it is the way to do it, because now the integral we're left with looks simpler. It's still, unless you have the formula to hand for this, it's still going to need integration by parts. So we'll have to go through integration by parts again, but at least it's easier. And after we do integration by parts once more, we'll just be left with an integral of cosine, which we should be able to cover. Do we get anything out of here? Well, you look at evaluating this at pi and 0, but in both cases, when you put in x equals 0 and x equals pi, you get 0 in both cases. Okay. When you put in x equals 0, well, there's a factor of x there, you get 0. When you put in x equals pi, well, you've got sine n times pi. Sine at an integer multiple of pi is, of course, 0. So this bracket here just evaluates to 0. So that doesn't contribute anything. So this, yeah, maybe write down the simplification line. So we've got a minus 4 over n pi times the integral 0 to pi of x. And now to prepare for the integration by parts, I want to rewrite that as a derivative. And this is the derivative d dx of cosine nx over n dx. But of course I get an extra minus sign because sine is the derivative of minus cosine. So I'm going to get an extra minus sign, so I may as well use that at the moment to cancel out that minus sign which has gone in the front. So this minus sign was written down because of this factor of -1 here. But now I pick up an extra minus. This should be minus cosine in here, but I'm going to bring the minus sign all the way out here and make the whole thing positive again. That look right? So we're left with this big constant 4 over n pi. We've got x. Actually, while I'm moving constants around, this 1 over n here, I might as well zoom that out as well. Make it n squared at the front. Just factorize it at this stage. So I've got x times the cosine of nx. This evaluated at 0 and pi. Then I've got minus the integral 0 to pi. And now it finally simplifies. Differentiate this x factor, it just becomes 1. And then I've got the integral just of cosine nx dx, which we'll be able to do. Now hopefully I was flying my minus signs around there, so hopefully I haven't forgotten any or misaccounted for any. I think it looks okay at the moment. Now, okay, so what survives here is coming from this first term. The integral here, of course, goes to some kind of integral of some sine nx over n, again, evaluated at 0 and pi, but of course that goes to 0. So this isn't going to give me anything. You integrate cosine nx, you get sine nx over n, but that gets evaluated at x equals 0 and pi, but this is always 0 at those points. So the integral there doesn't give me anything. What survives is coming from this up here. And just a round bracket there. So what does survive here? This is 4 over n squared pi times, well, when I substitute in x equals 0, of course, there's a factor of x here, so I don't get anything. So I only get something at x equals pi, and then it's pi times the cosine of n pi. So that factor pi there will cancel with that one. And what is cosine of n pi? Cosine of n pi, cosine of an integer multiple of pi. Okay, well, you're familiar with cosine. Cosine of an integer multiple of pi alternates between plus and minus 1. So you think of the unit circle in the complex plane, you're either out here on the east pole, so to speak, at the point 1, 0, where cosine is plus 1, or you're over here on the west pole, where at an angle of pi radians or an odd multiple of pi, and there cosine is minus 1. So it's an alternating positive and negative sign. It's minus 1 to the power of something. You just have to start it at the right location. So it's plus 1 for even n. Plus 1 for even n, minus 1 for odd n. So the index here we can have is simply n. Sure. The only thing to think, it's an alternating positive or minus sign, so it's going to be minus 1 to the power of something. Then you just have to make sure you've got it. Typically, these indices would either come out as n or n plus 1, just depending on which values of the index you associate the positive sign with. So. Okay, so what is this quantity here? This quantity here is an for any n. Okay, so we've got our a naught, we've got our an, so we can put them together and we can present the Fourier series. So we can say the required Fourier series is x squared, this is the function we're dealing with. It's a half of a0, which comes out as pi squared over 3, plus the sum over every n and is there anything I can pull out? So I can pull out the 4. And so it's going to be minus 1 to the power n. Of course, I can't pull out these other things because they depend on n, so they're changing, so they aren't common factors. The 4 is a common factor, so that can come out to the front. So this is the Fourier coefficient, and this is multiplied by cosine nx. So that's our required Fourier series. So we could visualize this and look at how, I mean, this is the infinite sum. When you're looking at the infinite sum, you've got exact equality with x squared. Of course, when you look at any finite partial sum, what you'll have here is the Fourier polynomial, it's kind of called, Fourier partial sum, which will be an approximation to x squared. As you make the partial sum longer and longer, it gets a better and better approximation. If you look at the little online demo attached to the previous lecture where we demonstrated the Fourier series for the square wave function, you can easily adapt that to put in change the definitions of the variables to put in the required form of the constant coefficient here, the an coefficient, the function x squared, and you could visualize the convergence of these partial sums. Before we leave this, we also note that we can, because of the presence of pi here in the coefficients and the simple enough function x squared, we can extract another interesting series for pi here. We can get another interesting series for pi from this by evaluating at x equals 0. So if we want to isolate pi and simplify the thing as much as possible, evaluating at 0 is a nice option because x squared at x equals 0 is simple enough. It's just 0. And these cosine functions, well, if we use x equals 0, cosine of n0 is just cosine of 0. That's got the very nice value of 1. So what does it gives us? It gives us that 0 is pi squared over 3 plus 4 times the sum n greater than or equal to 1 minus 1 to the power n over n squared. Well, this is an interesting expression which can quickly get a nice formula for pi squared. So not an infinite series for pi, but an infinite series for the square of pi. So what would it come out like? It would come out like pi squared. We move the other stuff over the other side and multiply across by the 3. It's going to be 12 times the sum over every n greater than 0. Now, when you move this sum over to the other side, it gains an extra minus sign, doesn't it? Move a term to the other side of an equation. You have to take the negative of it. Well, we've already got minus 1 to the power n. So when you take an extra negative, that would change it to minus 1 to the power. Well, you could either make it n plus 1 or n minus 1. Point is, it has to be one step either ahead or behind n. Let's make it n plus 1. Maybe the most natural. Sum over n squared. I.e., the square of pi seems to be equal to 12 times. So this is plus 1 for n equal to 1. Yeah. Minus 1 over 2 squared, plus 1 over 3 squared, minus 1 over 4 squared, etc., etc. So this interesting series with a very simple structure, just the reciprocals, the alternating series of the reciprocals of all the integers, plus 1 over 9, minus 1 over 16, etc. It's very simple series to write down, multiply it by 12, and hey presto, it gives you the value pi squared. Well, it converges to pi squared. 12 times that infinite series. Is that okay? Any questions about that example, or anything I could clarify for you on it? So the final lecture will be on, over the page on page 66, will be on the final section of Parseval's theorem. There's just one little thing to clean up here is if we look at section 3.4, that's at the bottom of page 64 in the notes. This is on, these are called half-range series. Well, okay, there's a little description there in the notes. And I'll leave you to work through the example there yourselves, but I'll just introduce it to you. These results about odd-even functions, the point we're emphasizing here is these results allow us some flexibility. If we are only interested in the function f on the positive domain. So what am I talking about here? So what am I talking about, this flexibility? So if you look at that example 3.8, it's dealing with this example of the function x, g of x equals x. Okay, nice simple linear function. There it is, 0 to pi. Okay, it's just a straight line graph of slope 1. Now, if we're interested in the Fourier series of this, now I haven't drawn it, what it's like over the negative part of the domain. Okay, remember, by convention, we set up these Fourier series on the interval minus pi to pi, using a change of variable. If you look back in the notes, using a change of variable, we can easily extend or contract this interval to go across any range. But we settle on the interval minus pi to pi. It's a good basis domain to use when we're considering the sine and cosine functions and their properties, because they're periodic with period 2 pi. So we see everything about cosine and sine, we see that in this interval minus pi to pi. So if we think about what kind of Fourier series for G we're going to get, well, okay, if we don't know how G is defined on the negative half, then well, we don't know what kind of Fourier series it's going to get. Now the most obvious way to define G over the negative half of the interval is to continue it as the same function, g of x equals x. Continue it as the same line. That would produce then overall this function would be an odd function. Okay, the function g of x equals x over the whole domain minus pi to pi is an odd function. And what we know about Fourier series now is that its Fourier series would be a sine series. There wouldn't be any cosines. However, we might also think about continuing it in a different way. So this is g of x equals x for x bigger than or equal to 0. This down here would be the function if we continued it as still g of x equal to x for every x less than or equal to 0. But we might also continue it as g of x equals minus x for x less than or equal to 0. Or another way of writing that would be absolute value of x. It's just another choice for how to continue this function across the negative half of the domain. I'm not, these are two possible choices for how to define some function on the negative half of the domain. But if we defined it like this, if we defined it so that overall the function was in fact the absolute value of x, that would be an even function. And so when we take its Fourier series, that will give rise to a Fourier series which doesn't have any sine functions in it. It'll just be a cosine series, just with some constant coefficient and some collection of cosine functions. Okay. So this is what I mean. This is what I mean by this flexibility idea. So by choosing the definition for this g, but by extension for other functions, if you're just presented with the function defined in the positive half, you can arbitrarily yourself make a choice about whether you're going to continue it as an odd function or continue it as an even function across the whole domain. So by choosing the definition for g, we can arrange g to be either, choosing the definition for g, across the interval minus pi to 0, insert that in. We can arrange for g to be either odd or even, leading to either a sine or cosine series, respectively. So it's just showing that we can have this flexibility and exploit it, perhaps, if for some reason we want to see a Fourier series consisting of only sine functions or only cosine functions. And if we're only interested in the original function on the positive part of the domain, then we're free to do that. If this is where our interest lies, it doesn't really matter how we continue it over the negative half. So so if you look at example 3.8 there, which concerns this function, previously we worked out the Fourier series for the function g of x equals x on the whole domain, minus pi to pi. So that was this single straight line, and there we found the sine function. So if you go through the motions again, go through the techniques, applying the odd and even function results, but instead work with the absolute value of x, you'll see you get a cosine series. So some constant term, which you can guess is going to be come out as pi over 2, because the constant term will always indicate the kind of average behavior of the function across the whole domain. So that should be pi over 2, I guess, in this case. And then a bunch of cosine functions. Whereas previously, the Fourier series for the whole function g of x equals x just was the sine series. Okay, so this also opens up all of exercises 3.2 to us now. Previously, maybe some of the later ones weren't available to us. So there's 9 questions there in total. So there's plenty of stuff to be working on there with exercise 3.2 in preparation for your next tutorial in this subject. Some of you had the tutorials, yeah, for your next upcoming tutorial. Yeah. So we have one more substantial lecture to give on this, on Parseval's theorem. So that will be, I'll be seeing you next Monday for 2 lectures, remember, swapping with Norman. So I'll see you this time on Monday and 2 p.m. I think. So we should finish off the Fourier series material then. Okay. Thank you. sign the signature sheet that's up here?
Yeah, I think a lot of the stuff you do is not. A lot of the questions actually you would explain the difference of energy efficiency and sensitivity.
Are you given any extra information? It's like this.
No, too many, not looked at yet.
Yes. But I mean, I know the idea with these processes.
Yeah.